Good morning, everyone. Today we have 4 press conferences, and we'll start with one entitled, Can We Undo Climate Warming? I'll remind everyone that the speakers will give short presentations, and then we'll open the floor for questions from the journalists here in the room, and also from those watching us via web stream. And those watching us remotely can ask questions on Skype by messaging EGU.media, or on Twitter by using the hashtag AskEGU. So I will introduce our speakers now. Our first speaker is Andrea Mcdonald, and he's a PhD candidate at the University of Victoria, School of Earth and Ocean Sciences in Canada. Hannes Bocher, sorry if I'm mispronouncing it, is a forest scientist at the International Institute for Applied Systems Analysis, Ecosystem Services and Management at Luxembourg, Austria. And Yuri Rogel is a climate scientist at ETH Zurich in Switzerland and an affiliated researcher at the IIASA, so the International Institute for Applied Systems Analysis. I'll pass on to our speakers now.
All right, so thank you for coming. I have a brief presentation summarizing some of my recent research. So jumping straight to the summary, from previous climate model analysis, it's known that if fossil fuel carbon is allowed to be naturally removed from the atmosphere, the models that we have suggest that 60 to 75% of the near-surface warming, so the global warming, will remain 10,000 years into the future. So given that naturally climate change is largely irreversible, I designed some emissions scenarios where you artificially go back to pre-industrial concentrations, presumably using some kind of carbon capture technology. So I used the University of Victoria Earth System Climate Model to simulate CO2 concentrations which are reduced in a mirrored path to the original increase until a pre-industrial concentration is restored. So this work hasn't been published yet, and I in fact only finished the model simulations once I got the notice that I was going to do a press conference. What the model is suggesting at this point is that more carbon needs to be removed from the atmosphere than was originally emitted by humanity, that a 20th century-like climate can be restored by the 24th or the 25th century under the middle-of-the-road scenario, and that by the 30th century, simulated air temperature is still above the pre-industrial temperature in all of our scenarios. So this is a diagram of the global carbon cycle, and I realize there's a lot of information there, but what I'd like you to focus on is the red numbers, and that's the human emissions. So humans currently emit about 9 billion tons of carbon to the atmosphere every year, and only about half of that remains in the atmosphere. The other half goes into the oceans, into the land. But that's a good thing now, because half of the climate change goes away. But if we are to reverse the process, then those other processes also reverse. So not only do we have to take the carbon out of the atmosphere, but the oceans will give back what they took up, and the land surface will give back what it took up. In addition to this, there's feedbacks within the system that aren't easily reversed. So the one that most of my research has focused on is the permafrost carbon feedback. So these permafrost soils have about 17,000 billion tons of carbon in them, and it's stored in the form of organic matter, so grasses and manures mixed into the frozen soil. When those soils thaw, that material decays and goes into the atmosphere as methane and CO2. But there's no easy process to put it back into the soil once it's rotted. So you also have to take that carbon out as on top of the human carbon that went in. So this is the model simulations that I noted in the summary. So here you see in the top plot, airborne carbon versus time. It goes out 10,000 years into the future. So the ocean does eventually absorb most of the carbon that humanity emitted. So 10,000 years into the future, about 60 to 70% of what was originally emitted. However, it also absorbs heat at the same time. So even though most of the carbon is eventually removed from the atmosphere, the surface temperature doesn't go down nearly as far. So these are the scenarios that I designed. They're based on the new RCPs, which are used in the forthcoming 5th assessment report of the IPCC. So they follow the RCPs up until the peak CO2, but instead of the RCPs, which just continue that concentration forever, they go back down in a mirrored path to the original increase. I also restore crop area, so agricultural area, to its pre-industrial extent, also in a mirrored path to its original increase. These are the preliminary results. So in the first plot, we can see change in temperature versus time out to the year 3000. So you see that there is some residual warming even after you have removed the CO2 from the atmosphere, especially in the high scenario. Ocean acidification is largely reversible, so it very closely tracks atmospheric CO2 concentration. So that seems to be some good news, assuming our model is anyway correct. In the lower plot, we see the sea level rise from the Greenland ice sheet in centimeters, not meters, centimeters. And it's largely irreversible. So you can restabilize the ice sheet when you drop back below about 350 parts per million. But the sea level rise that you've gotten from the ice sheet will remain for thousands of years and only very slowly be built back up into the ice sheet. And then in the top plot, we have the emissions with time. So as I mentioned before, human emissions are about 9 billion tons a year. In the high scenario, they go up to 20 before declining. And so in all of these, they eventually decline to zero, then very negative emissions, and eventually far out into the future, you can stop extracting CO2 from the atmosphere. So thanks.
Okay, good morning. In the next couple of minutes, I will present some results from a study that I carried out with an international team of colleagues. David McCollum, Andy Reisinger, Malte Meinshausen, and K1 Riahi. So it might not come as a surprise to you when I tell you that global mean temperatures have been rising in the past 150 years. However, where we'll end up by the end of the century is still very uncertain. Now, meanwhile, also the notion has been increasing that a gradual increase of the global mean temperature also means a gradually more dangerous world for humankind. And that's why recently, actually, international climate negotiations are trying to find a solution to keep warming below 2 degrees or below 1.5 degrees, as the most vulnerable countries are advocating. These limits are The importance of these limits becomes even more clear if you just keep in mind what Andrew told us just about methane that could be released at higher warmings. Now, the question actually, you see this huge range of uncertainty at the right-hand side, and it's clear that a lot of effort will be needed to stay below 2 degrees, but which uncertainties in this entire range matter most? That's the question that we wanted to look at. And so we have looked at uncertainties in 2 dimensions. One is the societal dimension at the left-hand side, the small man, and the geophysical dimension. Now, for the societal dimension, we have looked at different aspects of society. First, the availability of future mitigation technologies. For example, like carbon capture and storage, CCS, like nuclear energy, like biomass energy, or other types of technology. Another aspect we have looked at is how society will develop in terms of its energy use. Basically, how efficient a society we will have over this century. And finally, a last aspect of society we have looked at is the political dimension or political choices. How do choices in the next 10 to 20 years influence the ultimate result we can get? The geophysical uncertainties are compound from carbon cycle and climate uncertainties, but they are taken together as the uncertainties in the response in temperature of the climate system when relative to anthropogenic greenhouse gases. Now, I flip directly to our ranking of our uncertainties. What we found is that political action, or more specific, the timing of political action is the most important uncertainty if we want to stay below 2 degrees with a relatively high chance. That means if you would delay global mitigation action by 10 or 20 years, then the geophysical uncertainties would become irrelevant for the 2-degree target. For higher targets, for 2.5 and for 3, they would still be relevant, but for 2 degree, they would become irrelevant. Now, another finding is that societal uncertainties relative to energy demand or energy use have a larger influence than technological uncertainties. This is interesting because most of our current research is basically focused on technological on understanding better how the technological uncertainties will develop, which technologies will be available, will we have renewable energy, and relatively little effort is actually spent on those societal energy demand or efficiency research. Now, how did we come up with this ranking? For this, we basically used a couple of models, and I can give more detail about those if wanted afterwards. And we created this kind of cost-risk distributions. So what do they show? They show how on the x-axis, the horizontal axis, they show costs. On the y-axis, or the vertical axis, they show the probability to stay below 2 degrees. And they show how with increasing carbon price, climate risks are reduced. Now, an important feature of this distribution is that we find that from a certain carbon price onwards, so we don't get a significant improvement anymore in terms of reduction of climate risks. This is because of the committed warming and the timescales, the geophysical timescales of the climate system. So to assess the influence of the different uncertainties, we will then alter the assumptions that underlie this curve. And I will just illustrate this for the political dimension. This is how the curves change when we assume a 10 or 20-year delay in global mitigation action. As you can see, the curve shifts from the pink curve to the gray dashed curve. And we see that if we delay globally coordinated mitigation action in our model until 2030, then no matter how much money we are willing to spend at the problem, we hardly get more than a 20% chance of limiting warming below 2 degrees C. Now, what are the takeaway messages? Political choices over the next 10 to 20 years are critical. If the global target is really to stay below 2 degrees with a high chance, basically a strategy of delay linked to a stringent 2-degree target is never beneficial. The second, what I already pointed to, is that energy demand or efficiency measures have a larger influence than the uncertainty on supply mitigation technology, like the availability of nuclear or CCS. And finally, we also find that returning warming below 1.5 degree by the end of the century is possible in our model, but only with immediate action and in a high efficiency world. The results of this study have been recently published a few months ago in Nature, and more information can be found either in a publication or on my website.
Good morning. I will complement the previous talks a bit with some more concrete policy scenarios that we have recently run at YASA ESM. And let me introduce you to the topic of land use emissions with these few graphs here on the first page. When you look at the land use sector, there are some specifications we have to bear in mind. One is that the land use sector in the climate system can be sink and source. So we have management options that can produce sinks, so that lead to an uptake of carbon from the atmosphere, but also many that act as a source. And we have many small steering wheels, as you see here in the case of forestry activities, for example, where you can either enhance the sink or reduce sources. So it's a complex system, and we have tried with our models to assess land use options in this complex system, and what kind of implications these have in a wider context. So a result of these models are first the areas, how do land use areas develop in the future, and these are results for the EU countries in the baseline scenario. So here we don't have a carbon price and just have a business as usual scenario, so to say. And you see there are not big changes in the baseline expected. There's afforestation increasing, so the area with new forest is going to increase. And there is a category losing land. This is other natural land, so those afforestation is typically taking land from other natural land, partly cropland and grassland. But these are the major changes. But on the right-hand side, you see the emissions related to land use in the future, and you see there are much bigger dynamics than you could anticipate from just the area change. And this is largely due to the dynamics in the forest. You see the forest carbon sink, which is the lower line. It's negative, so this is a sink. And this is going to decline in Europe due to aging forests. And also it includes already the afforestation, so even the new forest cannot prevent that the forest is taking up less carbon in the future. So this we have to bear in mind. And then we have diminishing emissions from cropland, but also increasing emissions from livestock management, for example. So in total, the emissions are roughly staying at the similar levels in the baseline. If we now introduce a carbon price only at EU level, so that landowners have to pay a tax on emissions they cause, we get the following picture. And let me introduce you this figure. You see on the y-axis the carbon price we have introduced in US dollars, and then you see on the x-axis what percentage of the annual baseline emissions in the land use sector can be reduced by introducing such a carbon price. So this is simulating a policy measure where decision makers introduce a tax to change behavior of landowners. And you see there's quite significant mitigation potential, so we can reduce emissions in the land use sector by about 50% at a carbon price of $100, which is about 5% of the total EU emissions, by the way. So this is just to put this into perspective. And the largest potentials are actually in changing forest management. So concrete measures would be to reduce clear cuts and have more single tree selection and different other measures, and in livestock management. But of course, these mitigation measures have implications on the production. So you can imagine when you, for example, reduce in cropland management the input of fertilizer on cropland to reduce emissions from cropland management. You of course have impacts on the yields, on the crops that are growing there. Also, when you reduce the area of forest management in Europe, you have to still satisfy demand, and we are assuming that demand is not affected by these measures. So somewhere the material has to be produced that is consumed in Europe. We see that the potential reduction does not achieve large area changes. It's not achieved through large area changes in Europe, but it's really through measures like reduced fertilizer application. But what happens to the demand? If the demand is not changing, what happens then to production? And what is happening is that the production is simply pushed outside. As I said, the carbon price is only introduced to EU countries, not outside EU countries. And you see on this graph here, it's the same cost curve you have seen previously, but with a negative part to it that has to be added. And this includes the emissions that would occur outside Europe due to the shift of production to other countries. So food that is produced and was produced in the baseline in Europe is probably then produced outside Europe and affecting land use, causing deforestation and so on. That's all included in the red curve that you would have to add to the cost curve. And essentially you would reduce the effectiveness of EU climate policy. So the message is that this effect makes EU climate policies less effective, and it has to be added to the assessment. And you have, or decision makers should think about additional measures to take to reduce, for example, introduce a global CO2 price, or have sustainability standards for imports to Europe. Maybe also demand-oriented measures that actually then reduce demand instead of constraining supply. Thank you.
Thank you very much for the excellent presentations. We'll now open the floor for questions. Does anyone have questions here in the room? Or at home? Oh, yeah.
I'm Julia Rosen for the EGU blog. I have a question for Andrew McDougall. In your simulations, did you consider sea level rise from destabilization of the West Antarctic ice sheet?
No, we didn't. So currently, our model does include an interactive dynamic ice sheet model. However, we are still trying to couple in Antarctica. We don't currently have the ability to transfer ocean heat to sub-ice shelf melting, which would be very crucial for West Antarctica. So this was Greenland only.
Are there any other questions?
This is a question that's come from Skype by Andrew Planet. He asks, during the Carboniferous geological age, theories suggest that Earth's climate greatly cooled down by the fixing of the atmospheric carbon dioxide by trees in vast and never before occurring numbers. Could we strike a balance between creating atmospheric carbon dioxide by the burning of fuels and a globally managed mass-produced tree forestation plan?
So from what I know from literature, the general answer would be no. So the current amount of carbon in trees is, I can't think of the exact number top of my head, but it's on the order of hundreds of billions of tons of carbon. And through anthropogenic emissions, we could emit, in some of these scenarios, up as much as 5,000 gigatons of carbon. So there just isn't enough room in forests, even if you covered the entire planet in forests, to put that carbon into forests. And in the scenarios I did, 3/4 of the cropland was restored to forests. So I do take that into account as much as possible without, starving everyone.
Thank you. Are there any other questions? Julia, I know there was one on Twitter.
This is a question from a Twitter user. Is it correct to say that in a business as usual scenario, 20th century climate will be restored only in the 25th century? So I guess 500 years?
So from my understanding, the business as usual scenario is the RCP 8.5. So that didn't have restoration to a 20th century-like climate until the late part of this millennium.
Okay. Are there any questions from those here in the room? No? And are there any more questions on the web? Or should we finish here? Okay. So if not, thank you again very much to our speakers. Those here in the room are more than welcome to approach them after the press conference. We still have a few minutes, well, half an hour before the next press conference, which is at 11, and it's on thunderstorms and terrestrial gamma ray flashes. I hope to see you here again. Thank you.